All right, so today I'm going to talk about approximation algorithm. As you know, in reality, large number of optimization problems are NP hard. It means that it is not possible to design algorithms that can find exactly optimal solution in a polynomial time, of course. And the approaches for to solve these NP hard problems is that you could either use brute force, which has no guarantee on running time, and you may use some heuristics, which has no guarantee on quality of solution, and finally, the best of them is approximation algorithm. So you have guaranteed polynomial time challenge. And we need to prove a solution is close to optimum without even knowing what the optimum is. And of course, there are two different definitions for what we mean by approximation. The first one is absolute approximation, which means that there exists a k such that for any instance I, a star of I mean optimal value of instance I minus the value of instance I is less than equal to k. And we have relative approximation, which means that there exists k such that for any instance, the maximum of optimal value, a star of I, for instance I, over a of I, and a of I over a star of I is less than equal to k. And so let's solve a problem using approximation for a famous problem which is called vertex cover. So what is vertex cover? You have an instance, by an instance I mean just an undirected graph G equal to V and E, and your feasible solution is that a subset C, a subset of V, a set C subset of V is such that at least one vertex for every edge of G belongs to C. And the value is that the value of the solution is the size of the cover, which is this cardinality of C, and the goal is just to minimize that. Note that you have many vertex cover, so and also we have many feasible solutions, but some of them are optimal. And to give you an example, I will show you that, for example, you have node 1, 4, 3, 6, 7, here for example 5, another 1, 2, and 1. So 1, 5, 4, and let's see 6. So you see that the cardinality of C is 4, and this is a vertex cover 1, 4, 5, and 6. So the brute force approach is that you are just selecting 2 to the n different subsets from 1 to 3 till the n. And so because we are choosing 2 to the n different subsets to check, so the complexity is obvious, it is 2 to the n, which is not good. And that's why we try to show you an approximation algorithm for that. So the algorithm is just like this. You have, you set the set empty, and then you pick any edge U and V in E, and so you augment it by U and V. So you have counted that, and then you remove all edges that are incident, either U or V. Edges incident on either U or V from the set of edges. And then we repeat this process. We repeat till all edges are removed from E. And then we return your answer, C. So let me give you an example. So here we have 4, we have 3, we have 6, we have 7, 5, and 2. And for example, this is connected to this, 4 is connected, something like this. So C is obvious that you get 1, 2, 3, 6, 5, and 7. And so so you have 3, 6, you pick 7, you pick 5, you include 1, you include 2. And interestingly, the maximal matching is has just 3 elements, 1 and 2. So this is matched, this is matched, and this is matched as well. So we have 3 elements, 5 and 7, and the cardinality of the set M is 3. So it is obvious to see that the cardinality of C is just 2 times the cardinality of maximal matching. And because we assume that C star, the optimum vertex, of course, for this example, you can calculate it to see that it is just 4. And it is obvious that because the cardinality of C is less than 2 times C star, and C star must cover every edge in M, and hence C star contains at least one of the endpoints of each edge, and this means that C star should be greater than M, and then 2 C star. So we can conclude that this one is less than 2M, and M is C, and then it is obvious that C is 2 times M, which is less than 2 times C star. So we got an upper bound for C, so we approximate it, and it is 2-factor approximation. We call it in computer science, we've got a 2-factor approximation, and in other words, I can say the definition of C star, C, and C star, this is less than equal to 2. It means that K is equal to 2 by definition. And so we got 2-factor approximation. And the cardinality of C is less than 2 times the cardinality of C star. So because C is fixed, and for this example, we are so lucky that this example is so simple that we know the answer is 4. So this time it becomes 8, and 6 is less than equal to 8. So for that example I gave you, we get a 2-factor approximation. But this is very easy. And so let me give you another example, which is called traveling salesman problem, or TSP. In this new problem, we want to solve this problem using an approximation. So in this playlist of my videos, I just want to show you different examples and different approximations. There are, for example, a book written by Vazirani, and there are many books, around 4 or 5 good books about the approximation algorithm. Apart from the fixed parameter tractability, which is something else, which is more exact. And so here we are approximating. We don't have any exact solution. And these books are really good. So let me give you another problem, which is traveling salesman problem. And you know that. You visit every vertex exactly once and come back to your starting vertex while minimizing distance, time, or any other metric, indeed. So some of the weights of the edges, you have C of S, and this is the sum of the weights of all the edges. And we call it the cost of S. And you have S is U, V, V, and because you can count anything twice, so this is an example. You can count any edge twice or more. And you want to find a cycle which goes through all the vertices and minimize the cost of that cycle. And finding a Hamiltonian cycle and graph with minimum weight, a Hamiltonian path that is a cycle. So so when I say the cost of Hamiltonian is this. So we want to construct a path. So let's construct a path out of a minimum spanning tree. And first you find your minimum spanning tree, and then you rewrite it like this. You rewrite it like this, 4 and 3. And you do a depth first search, DFS. So your traversal is, DFS traversal is 1, 2, 3, 2, 4, 2, 1, 5, 1, 6, and 1. So it traverses all vertices. And of course, it is a cycle. And you delete duplicate vertices. For example, 2, I have seen 2, so this is a duplicate. 2 and 1, we have seen that. 1, I have seen that. And then you create a valid cycle, which is 1, 2, 3, 4, 5, 6, 1. And it is obvious that the cost of your cycle prime, which is the cycle that you have created, it is obvious that it is less than cost of the cycle. And because every edge is traversed twice, so C of cycle, this guy, C of cycle, the cost of the cycle is 2 times the cost of T. And so we conclude that C of a cycle prime is less than 2 times the cost of T. And this is bounded by Hamiltonian. So you have a Hamiltonian path, you have a Hamiltonian cycle, and at some point you cut an edge, and so you get spanning tree. You get spanning tree and call it T prime. Spanning tree, but it is not the minimum spanning tree. It's just a spanning tree. And the second formula that we can derive, which is obvious, is that the cost of your Hamiltonian is bigger than the cost of Hamiltonian if you just remove an edge. And we know that this is greater than C of your T. And so by combining 1 and 2, we get that the cost of cycle prime is less than 2 times the cost of your Hamiltonian. The proof is now complete. And so in any, we have NP-hard problems. And for example, real problems are NP-hard, are hard problems. And you are interested to find a fast polytime algorithm. And you want to have an exact solution, not approximation. You want to have an exact solution. So pick any two. For example, if I pick 1 and 2, it is called approximation algorithm, which is the subject of my lectures. And if you pick, for example, 1 and 3, it is called fixed parameter tractability, which is the topic of another playlist in my YouTube channel. And in that, I don't want to talk about it, but it is exponential in K and polynomial in problem size, which is n. And your parameter K is a function of your input. And if K is relatively small, we can still solve it. Of course, it takes time, but we can still solve it at a relatively good time. And so let me give you another example, which is K-vertex cover. So of course, this is the only example about fixed parameter tractability. Just to give you a flavor of what are these, I won't go into the kernelization and those topics. I give you an example. It is K-vertex cover, and the problem is that is there a vertex cover of size K? In other words, can we find the cardinality of your vertex cover to be less than K? So if K is equal to 1, this example shows you everything. So K is very, very less than the number of vertices. I mean, this is n. And so the brute force solution to K-vertex cover is that we try from n choose K. So we have n vertices. We want to select K of them, so it becomes n choose K, subsets of K vertices. And we test each choice for the coverage. And it is obvious that order of the running time is order of n to the K, and the exponent depends on K. So this is K. And the parameterized problem is fixed parameter tractable, in other words, FPT, fixed parameter tractable, if it can be solved in f of K times n to the order of 1. So this is polynomial in n, and this is exponential. Something should be exponential. And this is f of K is exponential. But K is not infinite, K is something. Exponential in K. And here the exponent does depend on K. So that was a very brute force algorithm. Now I would like to show you a another algorithm which is called